Steel reinforcement inside concrete can rust completely undetected for decades, then destroy the entire structure in months. A single bridge in the US costs $50 million to repair once corrosion reaches critical depth. By the end of this, you will know exactly why that steel rusts from the inside, why nobody sees it coming, and why the fix industry chose isn't the fix that actually works best. Rebar sits buried inside concrete, invisible by design. Concrete is alkaline, with a pH above 12, and that alkalinity forms a microscopic oxide layer on the steel surface called a passive film. That film is only a few nanometers thick, but it blocks oxygen and moisture from reaching bare iron, and it's the only thing standing between a bridge deck and a chemical reaction. The interesting part is that passive film works perfectly for decades, which is exactly why the failure, when it starts, is already advanced before anyone can see it. Chloride ions are the trigger, and they arrive from two directions. De-icing salt on northern roads and seawater on coastal structures both carry chloride, and those ions diffuse through the concrete's pore network at roughly the square root of time, meaning penetration slows on paper but never stops. Once chloride concentration at the rebar surface crosses a threshold, around 0.4% by weight of cement, it breaks the passive film locally, creating a tiny anode surrounded by a cathode just millimeters away. The reason bridges fail after 20 or 30 years and not 5 is not that the concrete resists chloride forever. It's that the chloride simply takes that long to migrate through a few inches of cover. Once the passive film breaks, electrochemistry takes over completely. Iron at the anode gives up electrons and dissolves into ferrous ions. Those electrons travel through the steel bar to a cathode site, and oxygen there combines with water to complete the circuit. The rebar becomes its own battery, and the concrete pore water becomes the electrolyte carrying current between anode and cathode. What matters here is that this reaction needs no outside power source at all. The bridge is generating the current that destroys it continuously, for free, using nothing but rainwater and road salt. Rust is not steel with a coating removed. Rust is steel with more volume. Iron oxide occupies up to 6 times the volume of the original metal, so as corrosion products accumulate around the bar, they push outward against the surrounding concrete. That expansive pressure cracks the concrete cover from the inside, first as hairline cracks invisible from the road surface, then as delamination where entire slabs of concrete separate from the rebar mat beneath them. The interesting part is that the concrete can look completely intact on a visual inspection, while the bond between steel and concrete has already failed underneath. Here's the part almost nobody expects going in. Corrosion doesn't announce itself with a warning sign, it announces itself with a sound. Inspectors walk bridge decks, dragging a chain or striking the surface with a hammer, listening for a hollow, drum-like tone instead of a solid ring, because that hollow sound is the only external evidence of delamination happening beneath an intact surface. There is no visible symptom until the deck is already structurally compromised, which is exactly why so many of these failures get discovered decades later than the corrosion actually started. Cathodic protection is the most direct countermeasure, and it works by hijacking the same electrochemistry causing the damage. Engineers attach a sacrificial anode, often zinc, or a specially designed alloy, or run an impressed current through embedded titanium mesh, forcing electrons to flow so the rebar becomes the cathode instead of the anode. What matters is that this doesn't repair existing damage. It stops new corrosion from starting by making it electrochemically unfavorable for iron to keep dissolving, which means it has to be installed before the structure looks like it needs anything at all. Epoxy coating took a completely different approach, and for 30 years it was the default choice for new bridge decks. A thin epoxy layer, roughly 7 to 12 mils thick, is fused onto rebar in a factory before it ever reaches the job site, physically blocking chloride and moisture from touching the steel surface. The reason epoxy-coated rebar became standard was not that it was the best long-term solution. It's that it was the cheapest upfront solution, costing maybe 15% more than plain black bar, while stainless steel rebar costs 4 to 8 times as much. But epoxy coating has a flaw baked into how it's installed. Any nick, scratch, or bend damage during transport and placement exposes bare steel at that exact point. And now that exposed spot corrodes in isolation, concentrated at a single location instead of spread across the bar. The interesting part is that damaged epoxy coating can actually accelerate localized corrosion compared to bare steel, because the intact coating around the defect traps moisture and chloride against that one exposed patch instead of letting it disperse. Stainless steel rebar solves the problem at the material level instead of the surface level. Chromium content, typically above 10%, forms its own passive oxide layer that's dramatically more resistant to chloride attack than plain carbon steel. And that resistance doesn't depend on an external coating staying intact through construction. The reason agencies avoided it for so long is not that it doesn't work. It's that a bridge deck built in 1975 wasn't expected to survive to see chloride penetration at all, back when road salt use was far lower and design lives were shorter. This is where the mid-video reveal matters, because it changes how you should read every bridge inspection report you'll ever see. Here's the part almost nobody expects going in. A bridge that looks structurally fine on every visual inspection can already have lost 20 to 30% of its rebar cross-section, because corrosion consumes steel from the inside outward while the concrete surface remains cosmetically undisturbed for years afterward. The economics explain why fixes get chosen the way they do. The corrosion protection industry spends over $300 billion annually in the US alone, and a significant share of that goes into infrastructure, specifically because concrete construction dominates bridges, parking structures, and marine works. What matters is the split in that spending. Cathodic protection and stainless steel represent proactive spending, paid before damage exists, while epoxy coating and patch repairs represent reactive spending, cheaper per unit but repeated indefinitely as damage resurfaces nearby. Agencies overwhelmingly chose the reactive path, and the reason is not engineering ignorance, it's budget cycles. A Department of Transportation evaluated on this year's spending has every incentive to specify the cheaper epoxy-coated bar today and let a future budget cycle absorb the cost of patch repairs 20 years out, even when a life cycle cost analysis clearly favors stainless steel or cathodic protection over a 50-year design life. Bridges built in the 1960s expose exactly this mismatch now. Those structures were designed with roughly 1.5 inches of concrete cover over the rebar, a specification set before chloride diffusion modeling existed in practical form, and before winter road salting reached its current scale. The interesting part is that the concrete itself, the compressive strength, the aggregate, the mixed design, is often still performing fine. The failure mode isn't the concrete aging. It's the salt exposure accumulating past a threshold nobody calculated when cover depth was originally specified. Modern codes responded by increasing minimum cover depth to 2.5 inches or more on new decks, which sounds like a straightforward fix, but runs into the same square root of time diffusion math from earlier. Doubling the cover doesn't double the time to corrosion initiation. Because diffusion scales with the square root of depth, doubling cover roughly quadruples the time before chloride reaches the rebar, which is why modern bridges with deeper cover are expected to outlast 1960s structures by more than a simple ratio would suggest. The repair cost curve is where all of this becomes unavoidable. Catching corrosion at the hairline crack stage might cost a few $100s per square meter for a patch and a corrosion inhibitor application. Catching it after delamination spreads across a full lane requires full-depth deck replacement, and catching it after rebar section loss compromises load capacity requires either replacing entire spans or closing the structure, which is how repair costs reach that $50 million figure on a single bridge. The reason this keeps happening is not that engineers don't understand corrosion. It's that the entire system optimizes for the cost visible at the moment of decision. A stainless steel rebar specification adds maybe 2% to a bridge's total construction cost, but requires convincing a budget committee to spend more today for a benefit that shows up outside anyone's current job tenure. And that mismatch between who pays and who benefits is the actual root cause sitting underneath every deferred maintenance backlog in the country. Given that chloride penetration follows a predictable diffusion timeline into a known cover depth, and cathodic protection retrofits can be installed on an existing deck before rebar section loss ever begins. At what measured chloride concentration threshold at the rebar depth should a bridge owner trigger cathodic protection installation instead of waiting for the first visible surface crack to appear?